Alright, this begins our second part of looking at location tolerances today. And let's see, get my technology running here. In this portion of the chapter, of the topic, we're looking at multiple features and composite features as well, the way we position those. So a lot of times, a lot of parts have more than just one hole, and those holes need to be grouped. And so the examples that we have in the book are like, generic kind of parts, so that we can focus on the dimensioning process and actually how it functions. Then your print reading, gets into real applications. There's some of that in your prints. So there's a couple of ways we locate multiple features. We use the rectangular coordinate dimensioning system, like so, when the holes are arranged in a rectangular fashion. This happens to be kind of square. Then there are situations where we have polar coordinate needed, like this flange or cap or whatever it might be, hub, and we have two basic specifications required for polar, which would be the diameter that the holes are located on, or shapes are located on, features, and then their spacing, whatever it might be. The single composite pattern, which is the simplest application for this, takes the series of holes, applies basic dimensions, so we have a framework established from our datums, in this case B and C. Then interpreting it, the meaning of it is these dimensions would be perfect, and attached to the center of where these dimensions 15 and 20 cross is a diameter tolerance zone that's basically cylindrical, and in this case it's 5/100ths of a millimeter at MMC, because we got that circle M thing going on, and then it's allowed to increase as it departs from MMC and goes all the way up to 0.85. So it's a huge location tolerance. So the center of the hole, of the pattern, that is, can actually locate all the way over. Okay, all the holes are checked together in a pattern. Okay, so these holes, by virtue of how these might be drilled, manufactured, they're probably going to end up in a pattern that is similar. But if you think about it, the center of this hole that's black right here, it could end up all the way over here. So that means the whole center would be right here, and so it would be, the edge of the hole could be all the way over here. Still be a good part. So it must be a very tiny, a pretty small shaft that would fit down in there, and still locate. So kind of exaggeration, I guess, is what I'm pointing out to you. The way they're doing their examples, they're exaggerating quite a bit so that you can see the difference, because in reality this would probably be a whole lot tighter, and the pattern as far as MMC, we might be controlling the size quite a bit. Instead of a plus or minus 0.4, it might be 0.04. Okay, so we have a smaller range to locate in. Now, locating features with separate requirements, there's really no example. I didn't look up one, but there's not one really. Basically, when we want to treat the patterns separately, okay, so when features in one pattern are different in size or have different location requirements, then we have to put underneath the frame SEP space REQT. So the only one they have is just this one here, where we have 14 this way. See, it's a circular part, so it's not using polar, it's using rectangular, and you'll see that a lot. And so these holes are located 12 basic off the center. Then these large holes are 17 off center, and then these are right on the center, and then these two holes are located at 14. So we've got, you know, 3 different basic measurements controlling where the holes are located. The pattern frame, if you will, is located. So to be sure that no one considers them all together, since there are different measurements, we put the SEP REQT underneath the frame. Then we can specify positional tolerance individually, and we use this when we have multiple datum references. We place a note next to the datum feature symbols and the related feature control frame to identify how many datum features and position tolerance specifications to consider individually. So we just put 2x individually, and there's really not a graphic for that. Okay, so basically just be aware of it. If you see it on a print, it's when we have multiple datum reference frames. Composite positional tolerancing, now that's on page 249. So let's see if I have a graphic for that. Okay, so basically here's the drawing. We have a pattern, okay, that's listed first. It's a composite positional tolerancing, and then a feature relating. Okay, so use one positional geometric characteristic symbol in one double height feature control frame. So that's this. Then we specify a pattern locating control in the upper part, and then specify feature relating control in the lower. So this upper part is controlling the pattern, how the pattern itself, which is basically dictated by this measurement and these specifications. So 20, 35, and then 18. You can see it's related to A, B, and C. The pattern is 18, and then to C, 20 and 35. Then the feature relating is actually the hole itself. So the pattern, you know, fairly large, 0.6 of a millimeter, 6/100ths of a millimeter, 6/10ths of a millimeter, and then 15/100ths of a millimeter for the feature. So when we put that all together and try to map it out, you can see what happens up here. The actual pattern, you can see they must always be 35 millimeters apart. Okay, but it's not controlled, does not have to be perpendicular, okay, to the part, as long as the centers are 35 millimeters. All right, so your shaded part right here is your feature. Okay, so at MMC it's 0.15. Then your pattern locating feature is a parallel zone, okay, of cylindrical, and it's at 0.6. Okay, there it is in the feature control. Here it is drawn out for us. So the hole can be oriented like this, which dictates its position by its angular shape. It can actually end up drilled that way in an extreme situation. And as long as that feature falls within the pattern, which the pattern can be located, as long as it's 35 millimeters apart and 20 millimeters holds the actual zone. So anywhere it falls in there, it's going to be 35 millimeters apart. So you're controlling the feature itself, and then you're controlling where it lands within the pattern. So here's the pattern circle right here, and then here it is down this way. Okay, so the holes, the pattern is held at 35, and so the hole itself, okay, is 35 millimeters apart, must be, but it can be inside of that circle anywhere, as long as they're held 35 millimeters apart. So, it's pretty goofy looking, isn't it? That looks like a really bad part to me. All right. So once again, they're using some extreme numbers here to show how they actually relate to one another in the real world. Of course, we're going to try and hold these holes as close to the center and more, closer to the pattern, of being across from each other, being parallel, and being perpendicular. So trying to, this is the basic perfect part that we're after. So that's how strange a shape it can become with this specification. So it's very important to control, be careful what's specified right in here so that you achieve what you're after. I really doubt that this would be allowable in the function, a real function of the part. Okay, now feature relating control must remain as a group perpendicular to the primary datum and parallel to the secondary datum. Okay, so let's look at this. Tolerance applied with two datum references in the lower feature control frame entry. Okay, so now we're able to control it and create this parallel zone, okay, that they must be with each other by specifying this. So that makes it look a little more controlled, doesn't it, by doing that. Okay, two single segment positional feature control frames. We display two position symbols, each in a separate compartment. Okay, like this. All right, we specify pattern locating control in the top, single datum reference in the lower half, provides orientation, and then a double datum reference provides orientation alignment for the feature, and then offers tighter relationship of the holes within a pattern, and a pattern locating zones and feature relating zones must remain same distance from secondary datum. All right, so when we look at this, and we've got two positions specified, it's making us look at it a single segment. So we can see we have a little tighter control. We're controlling based on this center line right here and keeping it on that center that's 18 millimeters away from B, so that the pattern stays within this location. So it's a little tighter control. Then we have composite positional tolerancing applied to circular patterns. Okay, using a basic diameter and a basic angle. Feature relating zones located partially or totally within boundaries. Okay, feature relating zones are located partially or totally within the boundaries of our pattern. It's held perpendicular to the primary datum and controlled as a group by basic dimensions. And the feature axes must fall within both zones. So our feature axis has to be within both of the zones that we establish. Okay? Kind of like the other coordinate method. So here we have that part we saw earlier. We have one single position tolerance, so it's considered all together. The actual feature axes must lie within both zones. Okay, so here's our part. There's the center of it. It has to be within this pattern locating zone, and the actual manufactured hole has to also fall within the feature zone. Okay, so we look around through here and we've got a 0.3 at MMC and a 0.8 at MMC. So we're showing our MMC, our minimum restrictive specification. So you can see it's kind of difficult to understand, but you got two center line circles, one representing the actual hole where it actually ends up, okay, and then the other one is representing the pattern, okay. So you have a center circle of the actual produced part, and you have a center circle representing how they're related as a pattern, okay, and allowed to have different tolerances. Creates this kind of control. So basically we would create a pin arrangement to check this part that would subtract the pattern and the feature control frame at its MMC, and if that diameter at MMC, which would be the hole at its smallest, okay, so it'd be 8. All right, so if it fits and we create actually a master part that mates up to this, that is off center its maximum amount, okay, from datum axis B, and if that master part slips into that manufactured part, it's a good part. We can easily check it that way. Then we can have two single segment tolerance applied to circular patterns. This allows locating pattern, locating, and feature relating zones from common datum axis, and displays a positional geometric characteristic symbol twice, and lists datum axis in both halves of the feature control frame. The top half of the frame controls the location of the features, just like the other, and then we add slot and tertiary datum to pattern located control to provide orientation of the pattern of holes. The lower portion of the feature control frame controls the pattern of features related to each other. So here's that situation. We have this slot, a notch, that's going to locate this part against something. And that center plane of that slot becomes our datum center plane C. Okay, so our pattern locating is related to C. Our feature relating is related to A and B. B is the center of the hole, and of course A is the bottom of the part, or the top of the part in this case. So considering all of that, your material condition requirements in composite positional tolerancing, the composite and two single segment feature control frames must have same material condition. You can't have one with a circle L, one with a circle M. And the datums must be in the same order of precedence. So we can't mix that up. We have to, since they're a pattern, they have to be considered related to datums in the same order. Coaxial features, anything that has a common axis like holes and counterbores. So when a tolerance is the same for both features, positional tolerance zone diameter is the same for both features relative to specific or specified datums. So your feature control frame appears below the note. So let's see. Let's flip to let's see if I can do that. I may have. Alright, sorry about the mix-up at the end of that other one. We're looking now at the coaxial features, so if you look in your book on page 255, anything having a common axis, which would be on, that's where it's presented, and on page 256 is a drawing. And what it means, it's a simple concept, but basically such as a counterbored hole shown there on 256, okay, where we got a 5 diameter and an 8 diameter counterbore. Then we can actually create a position tolerance and make the datum B with a boundary. This essentially creates a situation where we are to consider the diameter of the bore and of the pilot hole sharing a 0.25 position tolerance zone in this case. Okay, so that's the simple way to control the position of both of those. Most of the time that's drilled with a special tool 99% of the time, so they're going to be tightly controlled based on the precision of that tool. Then the facing page on 257, we can actually control each one separately if need be. If we have extreme situation where we need to control those, we can do that. So when we have different tolerances applied and they're just using a counterbore as a situation, one feature control frame appears under the note for the hole and one under counterbore. When tolerances control individual counterbore to hole relationships relative to different datum features, an additional spec is required. So you look on page 258 and see that situation, which is here. Okay, so we actually just place a note underneath the diameter that we're controlling, and we put it in the rectangular view to keep it separate, and that they must be considered individually. So when that is true, then it can be out of position like so. Looks pretty wacky, doesn't it? On page 258, where you've got the diameter, the long pilot hole, but then the control of the counterbore is allowed to fluctuate on its own and considered individually. So, coaxial position tolerance on page 259 for coaxial holes, used for holes lying apart and in alignment. So if you look on page 259, you can see the graphic for that, and here's a page of it included in the PowerPoint. So anytime they're separated by a feature, a hole or a gap, we consider them, but they have their own, okay, their own amount of error. So they're one coaxial feature control frame, but this allows each hole to be drilled or manufactured and end up looking like such. You know, it's kind of interesting looking, isn't it? How it could end up with this simple specification. This would be the extreme variation. So, composite positional tolerance for coaxial holes used when the tolerance of location alone is not sufficient to specify a separate requirement. The top half specifies the tolerance zones, and the lower half designates the tolerance zones in which the axes of the hole must lie within each other. Now look at it. By doing it this way, we now get these to be under tighter control and closer to being parallel and lined up with each other. Then there's composite positional tolerance for coaxial holes of different sizes. So we can do that. We have to put a note to coaxial holes. And so they're using a part that looks like this, okay, for positional tolerance of non-parallel holes. So basically, separate applied tolerances. No pattern here. We can also control how we locate the slotted holes. We use a bidirectional positional tolerance for a greater location tolerance in one direction. So when we specify that, we have direction this way, position tolerance, direction this way, position tolerance. That gives us this slot-shaped position tolerance zone by doing that. Okay, no extra notes or anything, but when you see position tolerance applied to a slot, it's creating a zone shaped like the slot itself. Then locating slotted holes. The size of each slot is within size limits, and precede the feature control frame with the number of slots. So 2x. Okay, so we don't have to dimension each one. We've got a wide zone on this one where the actual slot surface, slot location is allowed to position. Quite a big zone there on this one, but doing it to the extreme to show you how it functions. Then positional tolerance of spherical features is the last type of control, and that is on page 266. And we simply apply the S in front to be sure they know that this is a spherical shape, spherical diameter, and we put an S in front of the diameter symbol. So we actually have a little ball, and it's kind of difficult to show in 2D, but that's a spherical tolerance zone. So it's actually allowed to locate within a ball-shaped zone this amount. All right, we'll do the review in another presentation.